It's my pleasure to introduce Boris Murmann. So as I mentioned at the beginning of this session, we are spanning multiple disciplines in this workshop and in this session. We've talked about wearables, we've talked about neural architecture search. Boris, I don't quite know what you're going to say, but I think you're going to push that envelope a little bit for us. Thank you. Please take it away.
Yeah, thank you very much, Paul, and thanks everyone for inviting me. This is my first time at this venue. So I'm an analog circuit designer, and I'm only dabbling a little bit in computer vision. I'm not a pro, but I want to show you some of the work that we have done in the last few years, and it actually relates quite a bit to some of the things that I've seen in these presentations. Just a little bit general background. So I am interested in general in finding efficient ways of bridging the physical and the digital worlds, innovating in the cracks, building better interface circuits, and building better circuits that facilitate better back-end processing and kind of trying to fuse things together. And the end product in my group is very often a custom chip. So we're in the business of designing chips for many different applications, and computer vision is just one of them. So I want to start by giving you a quick outline. I want to highlight two of our previous works here. The first one was an attempt at near sensor processing that we did and published a couple of years ago. And then the second one has to do with an attempt of accelerating deep neural networks. And really what I'm interested in ultimately, and what I'll get to in the end, is how do I connect these two efforts in the best way? How do you actually get efficient computing and the right amount of near sensor processing combined? And hopefully we can have a good discussion about this. We start with the first topic. So really, I think from today's perspective, this is a blast from the past, because we started out by looking at handcrafted features, right? This was a common way of doing machine learning decades ago, but it turns out this is still attractive when you're thinking about hierarchical decision makings and always on type, low-end tasks. But even when you resort to handcrafted features and build relatively simple systems, one of the problems you have is this need of pixel-wise A to D conversion. So you take a lot of raw data, dump that through an A to D converter, and it goes into memory, where data movement is very expensive on the other side of the A to D converter. So the question is, and of course we didn't invent this, many other people have been working on this, is can we do the feature extractor before the A to D, right? And save some data movement energy in the back. As I'll say later, this may not necessarily reduce the total analog energy, but it is meant to prevent this deluge in the back of moving redundant digital stuff around. So the particular feature that we looked at was a histogram of oriented gradients. That was actually state of the art not long ago for handcrafted features. So we snapped onto this for this little study. And I don't have to explain that to you folks. I think you first make a gradient image, and then you turn that into histograms, and then you do inference based on these histograms. So one of the things you need to do here is you need to compute gradients, for example, a horizontal gradient and a vertical gradient between adjacent pixels. And one of the issues that comes up, and this is something that we have been zooming in particular, is that the gradients themselves have a high dynamic range if the image has a high dynamic range. So in a bright patch, the difference between two pixels may be a large number, may be represented by 300 millivolts. In a dark patch, right, if you multiply all the intensities by a quarter, say, that same gradient may be only 75 millivolts. So this is sort of visually shown here also. So if you have a scene like this, there may be a person in the dark, and the gradients around that body have a different magnitude than the gradients of the person on the bright piece of the image. So what it means is that you actually need to represent these gradients with relatively high resolution, or you will lose the information. And so the idea that we had and wanted to implement was to say, can't we do something more ratio-based? And this goes back a little bit into Weber's law and some of these fundamental ideas of perception actually being more logarithmic and ratiometric. Instead of computing the gradients as differences, shouldn't we compute them as ratios? So if you compute the ratio of two pixel intensities, you can actually, at least to first order, I mean, I'm not getting into noise issues and things like that, but to first order, the illumination actually cancels out and you become illumination invariant. So you may ask why this is a good idea. Well, the whole point is to drop the dynamic range that comes from illumination variations across the image. Because once you calculate these gradients as ratios, what you can do is actually quantize very aggressively. You can, for example, quantize these gradients now into 1.5 bits, where you say, well, there's either an edge or there's a negative edge or a positive edge. And it doesn't really matter what the illumination is, because that canceled out before you hit the quantizer. So the high dynamic range of the image itself actually doesn't require extra step in these quantized ratio. So we experimented a little bit with 1.5 bits, which means 2 levels, and 2.75 bits, which means 6 levels. And I'll show you some results on this. So the other nice thing is that you not only now save bits in terms of what you need to express these gradients, you can also compress the histograms now, because the histograms have a much smaller library of entries, and they can be compressed in a very efficient way, it turns out. So we found out at the end of the day, the net benefit you get from this ratio feature is that you get about 25 times less in HOG feature data compared to a standard 8-bit image for which you would take linear gradients. So here I want to show a little bit some of the experiments that we did on the effectiveness of this coarse quantization. So this is just the baseline. When you take a linear 9-bit gradient of an image and you vary the illumination, that's what I did on the x-axis here. Well, the average precision, this is an object detection task, it's relatively stable within a range, but then as expected, you know, it would drop off if you get too dark or if you get too bright. And here on the right side, you see the illumination changes. At some point, you just saturate the image or you lose some features. And so with 9 bits, you're doing reasonably well. So now if I tried and I aggressively tried to quantize these linear gradients, things look very bad because, well, the range over which this works goes down because what I discussed previously, you're losing a lot of edges in this image that have a different exposure and so on. But now if we drop in the idea of using these log gradients or ratiometric features, the features become illumination invariant, and you see here the gradients actually look the same no matter what the illumination is. And yeah, lo and behold, you actually get a very good performance for across the illumination. When things get too bright and you saturate, everything dies, but that's to be expected. So there's a small difference here between 1.75 bits and 1.5 bits and 2.75 bits. And that just has to do with the fidelity of the gradient. So it depends a little bit on the application, on which one is good enough for you. So we always build chips out of these studies in the end to make the rubber hit the road. So what we did here is actually not as fancy as some of the things that I've been seeing here. We started out with a vanilla 40 pixel array. So these are regular imager pixels, 40 structure, 5 micron pixels. And then whatever we bolted on actually sits in the periphery. So we have a 3-row buffer. You need an analog buffer if you want to calculate analog features. So we have kind of a 3-rank memory that allows us to store these and then do computations with them. I'll show you how that's done in a moment. And then we mux this out, and then instead of going into ADCs, we call these RDCs because they're ratio to digital converters. We also, just for debugging, we had a raw image output just to see if this whole thing works before we do any computations. Here's some of the circuitry for the analog designers. Of course, in an image sensor, you have, you know, very skinny columns. So these readout amplifiers, they're very minimalistic. And so the way the computations are done is that for each row that you want to process, there's a separate storage capacitor. And then, right, you kind of average between these to do your computations. And then we have a 4th row to allow for some image pyramid computation. So this is a little bit beyond the scope of this talk, but I just wanted to mention it as an aside. Snapshot of the ADD converter for people who design ADCs. This looks reasonably familiar. It's basically a successive approximation structure, but instead of subtracting the converted result from the input, you're actually dividing the input. And this is actually a very easy way to build kind of a ratio ADC. Log ADCs in general are pretty difficult to build. Try to build a 12, 14-bit log ADC. That's very difficult to do. But this 1.5-bit or 2.75-bit log is actually easy to do because it's just a couple of successive divisions that you can implement in this feedback network. So here's a summary of this. We can chat about more details if you're interested, but we have this chip. It's a normal CIS process, 5-micron pixels, like I said. And this imager per se is not setting any record performance numbers. The energy or power dissipation is what you would see from a vanilla imager with a given dynamic range. This was kind of a 60 dB dynamic range design. It's not extremely large, but decent. And so that runs at a couple hundred microwatts. And so the benefit really that we wanted to demonstrate is that the data that this thing pumps out can be highly compressed and save you in computation and memory access. And so we quantified that one in just the raw HOG feature data compression, which is 25x. And then we tried to estimate this. We didn't build this deformable parts model detector at the end, but we think that you get at least a factor of 3 in power savings because there is less data coming in. There's more compressed data coming in. All right, so one thing that inspired us ultimately about these 1.5-bit log gradients, it seems like they're preserving information really well. And here, Julian, he's probably watching, helped us a little bit with this. You can take an image and then you make 1.5-bit log gradients, and then you can actually try to reconstruct this image based on the gradients with a simple algorithm. It's remarkable how much information you actually preserve in these log gradients. Of course, you lose some. This is lossy, but it looks very, very good. And so we're wondering, hey, why don't we ditch this deformable parts business and HOG and so on, and really try to connect this effort now to deep neural networks, which are clearly winning the race nowadays in terms of classification accuracy. And so ongoing work in my group now says, what would it be like, or what would happen if we dumped these log gradients into a CNN? And so here's a little Mickey Mouse experiment that we did some time ago. Instead of using a regular image, we take a log gradient image and we train a neural network. We can train it in different ways. Here's an example that just says, train it such that at higher levels of the CNN, the L2 distance between the high level features are minimized. Train these new filters that act on the 1.5-bit gradients to minimize that. And we get remarkably good results. And so this has now motivated me now to launch a deeper study. Unfortunately, I do not have conclusive results on this yet. But what we're trying to essentially get to is that we want to get into a position where the first layer of the neural network is heavily quantized, right? This is not possible in a normal neural network, for data and energy savings. And also, and this is also something where I'm still collecting data, is that it seems there's a complexity reduction possible in the neural network. So we have some results that showed that a neural network that is shown log gradients may need fewer filters in the first couple of layers, simply because you have the whole dynamic range collapsed of the image. So I don't have hard data on it yet, but I'm sort of dying to establish this thoroughly and publish on it at some time. Okay, so now I want to shift gears a little bit and want to show you the second line of work that I really want to get connected to the first one, and this is the work in progress. All of you know how CNNs work, right? It's a massively parallel compute operation. The computer architects call this embarrassingly parallel. What's a little bit annoying, and I just said that, is all but the first and the last layer can be aggressively quantized. And so people have been looking at ways to make these operations lower power. There are definitely digital CNN people here in the audience, so I want to make fun of them a little bit, right? I mean, the digital approach, and we've seen that on the previous slide as well, is you're shuttling a lot of data around between different memory hierarchies, and then you have these processing elements that give you a good amount of parallelism, but not enough to do all the computations in one shot. So every time you compute something, you're hitting some piece of memory, let it just be a register file. You can very easily show that there's a strict upper bound that you get from these architecture just based on data movement. Forget the energy it takes to multiply or add, it actually doesn't matter. It's moving the data to these multiplies and adds is what limits everything. And so we see in current, even highly optimized digital accelerators, crossing 10 tops per watt is actually very difficult because of this. So my group asked the question, well, if we make something that's probably not as programmable as other things out there, and maybe a little bit smaller, right, for direct processing of small image sensors, always on type applications, can we just unroll this whole thing and just eliminate most of the data movement? And this is what the idea that we had in building what we call a mixed signal binary net, where we unroll all the input activations into a long vector, say 1024 wide. We unroll each filter completely, and then we have heavily quantized implementation, 1-bit multiplication with XNORs, and then accumulation with switched capacitors. And so here you basically have input volume, filter volume, and here you get that dot product pixel out. And everything happens in one shot in parallel without any data movement. And the weight is local, so it's a weight stationary architecture. So this is a fully unrolled circuit, mixed signal that performs all of this in one shot and with very little data movement. So we made a chip out of this. So this is not, as of now, I mean, we are working on more sophisticated prototypes now, but this wasn't good enough for ImageNet, but it could handle CIFAR-10. This is kind of an 8-9 layer network with 2x2 kernels. And really the contribution here was to show that you can get to energies for CIFAR-10 as low as 3.8 microjoule per classification. So this brings you under a milliwatt, even for hundreds of frames per second. This was done in a reasonably advanced process, not extremely advanced. So even by today's standard, I haven't updated this chart in a while, but this is pretty much one of the most low energy implementations there is at the CIFAR-10 level. The accuracy is a little bit held back by the 2x2 filters. We made a mistake. These really should have been 3x3. But this number of a handful of microjoules per classification is much lower than whatever you get from other custom processors. We built a digital version of this as well, which came somewhat close, but still isn't quite as good. So now here I want to maybe start sort of the discussion a little bit. So clearly my objective, I said it in the beginning, is now to join these two efforts. I'm actually interested in bringing the physical image closer to the DNN computation. And I just want to highlight the way this is done right now is actually somewhat ridiculous in my mind. And the previous talk pointed this out already. Someone takes pretty images for a few years. They go through this ISP that does tone mapping and all these things. And it spits out these beautiful JPEG images that have nothing to do with what the sensor actually detects, more or less. And then we take these visually appealing images and we let go a few million DNN designers, and they're trying to squeeze these DNNs until nothing is left in the lemon, right? And I think we've reached the end of this pretty much, and I don't know what the benefit is anymore. You now actually start seeing papers where people say, oh, we have these super optimized DNNs based on this flow, and now we connect that stuff to a sensor and it seems to be falling apart. Well, this is not surprising because you're not training with real sensor data. You're training with these images that have perfect angles and illumination and so on. In a real world application, you don't get that. So I really want to get more into this flow below where you have real sensor data sets, not pretty JPEG images, but actually raw images. or log images of some sort that are more physical, with varying amounts of illumination across the images, occlusions and so on, different angles, something that a real sensor would see. And that's where a lot of these things would be used, maybe on robots and so on. And then we should engage in a joint optimization of this. And definitely it's not going to be a general ISP that makes beautiful images. It should be something else between the image sensor and the DNN. Maybe a log is enough. I think maybe some of you have some good thoughts about this, but you clearly need something between this and the DNN. But this should be jointly optimized based on real data. So this is sort of where I am. Based on my first couple of exposures to this field, this is where I want to go. So I'm going to sum up with that. So I have dabbled in feature extractors that are near the sensor, not really in the pixel. And then we played with low power mixed signal DNNs, and these two things have a clear connection point. But for me to make more progress, I want to get to a more holistic, less siloed view of this whole processing pipeline that doesn't run on pretty JPEG images. I'm actually working right now on making a data set if someone has ideas on how to best do this for real world images. It would be fun to chat. And then I want to encourage kind of the deep learning community to stop optimizing this DNNs based on artificial data sets. I mean, it's great for winning competitions and things like that, but we should ask what happens in the actual application and see what is needed to perform well in the real world context. I think we've learned enough about the fundamentals now to kind of think more about the real world. All right, but this is all I had. Thanks again for having me. We'll be happy to chat with you folks now.
Thank you very much. That was really exciting. Please, another round of virtual applause. Listen. Thank you, that was great. I'd like to remind anybody who's watching on YouTube, please, there's a YouTube chat and I invite your questions there. In the meantime, while you think about that, I hope perhaps that there are colleagues around the table in the Zoom call who have questions for us. While you think of that, I think it's my job as the session chair to think of something. And I was really inspired by your talk to wonder what happens if we push it a bit further, almost to pre-sensor processing. So very commonly in an image sensor, we have things like a Bayer mask. We can also think about the properties of the photodiode, including dynamic properties. I wonder if you have thoughts on how we would optimize at that level for, well, understanding rather than image capture.
Yeah. So this is not really my domain. I agree with you. This should be looked at, and I think several people are, right. Gordon Wettstein at Stanford, Julian's advisor, is working on this, and I think it makes a ton of sense to explore this and basically make it a part of the whole deep learning training pipeline, right? If you have such filters available before the image sensor, you can probably train them very nicely. And yeah, that is a zero power first layer, basically, right? That's the attractiveness of it. And yeah, I think the jury is out in terms of what will this look like cost-wise and so on. I think scientifically, I think it's a no-brainer to pursue that. We'll see if the industry will adopt it. I guess that's where I have the most questions. How economically feasible is this? And I don't know enough about the technology to judge it.
Thank you. Yeah, absolutely. Well, Terrio, I think you have a question. Would you like to speak up?
Yeah, no, thank you so much, Boris. Super interesting talk. I echo what you're saying about being truthful to the actual applications and using real signals. My question is, what are the actual applications that you are looking at that will be informative enough for us to show to others that this is the way to go?
Yeah, I think robotics is a domain that seems appealing. I don't know if this will really be the ultimate killer app, right? Who knows what they are in 10 years, 20 years. But I have found that, I have a reference here. There's this paper on Open Loris. These are some robotics people that actually developed a very nice sensor data set with the kinds of features that I like. So I find that the robotics people are the most open to this problem right now. I don't find enough people in computer science who want to look at this. So I'm kind of clinging on to the robotics myself a little bit as an application. I mean, I bet there are, applications in the commercial world, right? Putting these sensors on AR type devices and so on. But these are still emerging a little bit and are abstract and kind of owned by the Facebooks of the world, right? We had a talk about this, but I think it's going to be robotics for me.
Okay, that's great to hear. Thank you.
I mean, in a way, I think that's more or less what you're doing with these little autonomous cars and things, right? I mean, that looked very nice to me, actually, as a good example as well, right? You get real signals and they're vibrating and the illumination is all over the map, right? I think this is the way to go to make this stuff work.
Thank you.
Yeah.
Thank you. I think we have another question, which has been typed in the chat, but Edward, you're on the call. Perhaps you'd like to speak up and explain your question.
Yeah, I guess the question, so you had these fixed function convolutional kernels processes that you were doing. I was wondering how difficult would it be, or are the kernels that you can run changeable dynamically? And
yeah,
then how difficult would it be to have the output go back into the array?
Oh yeah, it does that. So this is a very cartoonish schematic. The output activation. So we basically compute one layer, and then the outputs, they feed back as input activations again. We actually sequentially compute a number of layers with the same neuron array, basically. And inside the neuron array, these weights are programmable, and in fact, they get reloaded from layer to layer. So here you see SRAM. So we do a bunch of computations. So there's basically this weight stationary memory, or sort of quasi weight stationary memory in the center. And once we've done a number of computations, we reload these weights from the SRAM. So I think it does everything you asked. And it is actually kind of semi-programmable, I would call it. We can run a varying number of layers, and we can change a few things. It's just not a super programmable processors as the CS people would normally be used to. It's a little bit limited in terms of what you can.
Yes, my theory is that the SCAMP device, the analog side of the SCAMP device, every instruction can be thought of as a convolutional filter.
Mm-hmm.
So perhaps if you can encode the same filters into this, then you are actually working with parity in terms of computational ability. But perhaps you're doing it in a more efficient or different way that gives us other benefits. Yeah.
I mean, except that this is not integrated in the pixel, right? So that's the difference. Yeah. And I think I'm very interested in pushing some of this stuff into the pixel as well. I mean, the main issue here again is this thing is power efficient because we squeezed it down into binary computations. But when you're in the pixel, well, you have a high dynamic range signal. You can't just binarize that. You've got to do something before that. And this is actually where these log gradients may come in again, right? I mean, maybe this is something that really helps us. This is kind of the hope that we can get a feature that can be highly quantized for this type of local processing, so that we don't have to slush all these bits around and make the pixels bigger than they may need to be. Yeah.
Thank you. Is there another question? In that case, I think I want to try and ask another, perhaps off the wall question. Back in the dark ages, analog computers were really popular, but typically they were continuous not only in terms of the signals, but also in time. You would actually solve a differential equation by setting up a circuit that actually implements the differential equation. And you could do this in a sensor array with the signals as you capture them. I think there is some work by Chua and Yang on this kind of thing. I wonder if, Boris, you've thought about this kind of thing and what you think the opportunities might be, or why perhaps this work has been neglected.
Yeah, I think the number one issue is the accumulation of noise and other non-idealities. As in all large, this is why we do digital VLSI, otherwise there would be a blooming field of analog VLSI. This is really the problem. In fact, it's funny you mentioned it. I'm actually working on such a system right now, but it's not used for this application or for some other meaningful signal processing application. It's actually more used like a random number generator because of its features to mix up all kinds of random issues. So it comes for a hardware security problem I'm working on. So I think this is really what killed this idea. It's mathematically beautiful. And there is some interesting work out there you may have seen from Yanis Tsividis and others where they use systems like this to get a rough solution for a differential equation. And then they let a digital computer refine it. So I think whenever you have a low fidelity application, I think there's merit in these approaches. But once it's high fidelity, it should not be analog. I should point out here, there's one important feature about this structure that we built, and that is there is very limited analog here, actually. So we just accumulate in the analog domain, and then we slice this result. It gets regenerated. This is actually important in any computation, that after a few stages, you want to regenerate. You don't want to propagate the noise, accumulate the noise from stage to stage. So yeah, I think this is my message to everybody in analog computing. You gotta, at some point, you gotta slice it, regenerate it, and then move on, right? So that you don't do analog noise accumulation.
Well, when we regenerate, we have to classify.
Here it's really quantization. So, so if you get by, and neural networks are okay with that, right? We know that even in relatively sophisticated neural nets, 2-3 bits go a long way. So yeah, that's been the general approach that we're taking here.
Thank you very much indeed. I think that probably takes us to the end of the time. Another round of applause for all of our speakers from this session. And we should move swiftly to the next part of the agenda,